In this lecture I want to introduce a very important concept in signals and systems. This is in the context of studying linear time invariant systems, LTI systems, and it's the concept or the idea of decomposing a time function, say u of t, into an infinite sum of impulses. So we're going to decompose it in time. This is a complementary but very different, fundamentally different decomposition of a time domain signal compared to frequency decomposition, which is really the essence of Fourier series, Fourier transform, Laplace transform type analysis. So you have a, let's say we have a signal that varies in time, and we'll call it u of t. And if we decompose it, so we can decompose it according to a sum of e to the j n omega naught t. Okay, that would be series, Fourier series decomposition. All right. We could also sum it as e to the st. All right. And of course this ends up, this sum could equally be an integral, so for, I should just put integral. So this would be Laplace transform, right? And Fourier transform would be e to the j omega t, but where we're actually integrating, our sum really becomes an integral. But in all those cases, the decomposition is all frequency decomposition. Okay, what we want to do is we want to do time decomposition. And here's the idea. One way to decompose this signal in time is to take pulses. So if I can take a pulse and I can add it, and say this is at time 0, and I can add it to another pulse that's slightly after 0, and another one that's a little further after 0, and maybe it has a little different height. Okay, and you can add those all together. This whole thing could equal some function that basically is stair-stepping. Right? And although my diagram doesn't show it, the steps should all be equal width. Okay, so it would be, here's a step, here's a step, here's a step, here's a step. Maybe there's two steps that are at the same value here. Okay, and so we basically are summing pulses. The width of each pulse would be the same, and we will refer to that as capital delta. Okay, and of course this is an approximation. This cannot, if capital delta is a finite width, non-zero width, we cannot exactly equal u of t. What we might have is, we'd call it u of p, okay, because p for pulses. So it's an approximation of the original function. However, if our width of our pulse approaches 0, then in the limit, then u of p of t will approach the actual function u of t. All right. So at some point, delta gets small enough, we won't even be able to distinguish one little pulse compared to the next one, because they'll be so crammed together. And in the limit that the delta is 0, the u of p will become a continuous function that will equal u of t, and that's what we want to develop here. But the thing to remember is the way that signal u of t will have been decomposed is not by frequency components, but it will be decomposed by pulses. Okay, so let's begin by describing a pulse, and we'll say that it's centered about 0. We're going to call it P sub delta, capital delta. And it's going to have a height of 1, and it will have a width of capital delta, and it will be centered about 0. So we would write P sub delta of t is equal to 1 for t greater than minus 1/2 delta and less than plus 1/2 delta, and it's going to be 0 otherwise. Okay, and we can write our function u of p, right, this approximation, as an infinite sum of these pulses. Okay, but they can't just be a piece of delta evaluated at time t. They have to be time shifted versions, right? Because we'll have a pulse, for instance, we'll have a pulse here, we'll have another pulse after that, another pulse after that, and if we're going to sum an infinite number of these, as we sum each one, we have to make they're not all occurring at time 0. They occur at 0, they occur at time delta, at 2 delta, 3 delta, and so on. Okay, so we're going to time shift this. Actually, let me put our index n. This is going to go from minus infinity to infinity, because u of t might occupy plus and minus infinity time. So P sub delta of t minus n capital delta. All right. So for instance, consider P sub delta t minus 3 delta. What does that look like? Well, here's our axis with time. Here's 0. We have 1, 2, 3. 1, 2, 3. This looks like, and I'm sorry, that's 1 delta, 2 delta, 3 delta. Okay. So we have a pulse that's a unity height, a width of delta, and it's centered around 3 delta. All right. So we are going to sum. We have an infinite sum of these pulses. At this point, okay, what this evaluates to is just a value of 1, right? Because each pulse lasts for capital delta time and has an amplitude of 1. So you put an infinite number of those that are time shifted, and you end up with just a constant of 1 for all time. Right? So that's not what we want. I mean, it's a good beginning. We need to weight those pulses now so that we can follow u of t. So we'll multiply it times u of t. However, we actually don't want t, because if we're going to assemble these pulses, we want the weight, okay, the amplitude of that pulse to stay fixed for every capital delta period of time, right? So we need it to stay fixed, like for this plateau here of delta and this one and this one, right? So what we're going to write is u of n delta. Okay, that's the time at which we're going to evaluate u of t. Okay, so that's our function u of p of t, and it will look like basically steps, right? And it will follow our u of t. Okay, so this would be u of t, and the black one here is u of p of t. Okay, so now what we want to do is we want to take the limit, we want to shrink delta, we want to make it smaller and smaller, because we're going to get a better approximation at that point. Remember, the whole goal here is we want to accurately decompose u of t by an infinite sum of time domain. We want to decompose it by time into an infinite sum of pulse functions. All right, that perfectly replicates u of t. We don't want an approximation. We want to do better. So what we're going to do is play a little manipulation here. We are going to, we're going to take the limit as u of p, as delta, capital delta, goes to 0 for u of p. And so we'll take the limit as delta goes to 0 of this sum n going from minus infinity to plus infinity. Now I'm going to do a little trick here. I'm going to take u of n of delta, put that there first, and then I'm going to pre-multiply the pulse function by 1 over delta, capital delta. And then I'm going to post-multiply it by delta. I haven't changed anything because the 1 over delta times delta cancels out to 1. So I haven't changed anything, right? But this is going to be useful here. So let me step aside from this problem for a moment and let's consider the following. Okay, so if we have some function that is going to be summed, let me write n from minus infinity to infinity, of some function f of n delta, okay, times delta. All right, if we take an infinite sum and we're going to take the limit as that delta goes to 0, all right, you find that that actually becomes an integral with where the function is a function of a continuous variable. So let me write that it'll be integral from minus infinity to infinity of f of tau d tau. And what has happened is that del becomes our differential term d tau, n capital delta becomes our continuous time variable, our continuous variable tau, and the sum becomes the integral. Right? Recall, I mean, the integration is just ultimately is the area under a curve, right? And this infinite sum is we're taking the height of that curve, f of n delta, times the width of that particular segment of the curve, multiplying it, and that's the area, right? And then we're going to sum that overall time, or overall the full space of the independent variable there. So as delta goes to 0, we're actually evaluating the integral. So we're going to put that to use here. So let's return to our u of p function, and what we're going to find, you notice that what we have is here we can think of that as our f of n sub delta, right? We have actually this form of an infinite sum of f of n delta times delta. So let's rewrite this. So the limit as capital delta goes to 0 of u of p of t is going to be equal to the integral from minus infinity to infinity of u of tau, okay, times, and now we have a problem in our parentheses here. Let me skip that for a moment and complete the statement. Tau over here, or I'm sorry, capital delta here is going to become our differential d tau. But the question is, what do we put in here? Okay, we have this problem that 1 over delta goes to infinity, right? As delta goes to 0, 1 over delta blows up. So let me draw what's going on here. We have a pulse, 1 over delta, p sub delta, t minus, and let me leave, actually for the moment, let me leave off the n, the time shifted version, okay? That's not needed to make this the substitution that we're going to make. Okay, so the height of this guy here now is 1 over delta, right? And the width is delta, right? Because by definition our function p sub delta has a width of delta and an amplitude of 1, but now we're scaling it by 1 over delta. So notice that the area here, area equals 1. In fact, the area equals 1 regardless of delta size or width, right? As you make it skinnier by making delta smaller, 1 over delta gets taller, right? And the product of the two, 1 over delta times delta, remains unity. And because this function now is part of an integral, is a part of an integrand, the only thing that matters when a function is part of an integrand is ultimately the area of that function. We don't care about, it's not so important what the value is of that function at any particular point in time. It's the area that matters. And so, although we cannot describe what's actually happening at time 0 if we were to allow delta, capital delta, to go to 0, right? Because at that point, capital delta going to 0 would mean the amplitude of this function blows up, right? So it's actually undefined at 0. It has a 0 width, and yet there's a finite area. It has an area of 1. So we're going to define that as this delta function. Okay, so define. So I'll come back and fill this in a moment. So where we're going to define this lowercase delta, okay, as being equal to the limit as capital delta goes to 0 of the function 1 over delta p sub delta of t. Alright? So you get the idea? This delta function, okay, delta function, or Dirac delta, as it's called in physics, I think. This function has 0 width. So 0 width, infinite height or amplitude, and finite area of 1. Okay, it's a bizarre function. It isn't actually defined. It's 0 for all values except for at time 0, and at time 0 it's undefined, and yet it has a finite area of 1. Alright, so we're going to use this up here, and we're going to say this is times delta. Actually, it's not going to be just delta, little delta of t. It'll be, remember, this was a time-shifted version. Let me go back up here. Notice that it's a time-shifted version here. T minus n capital delta. So what we need to do, remember, the n capital delta gets replaced by the continuous variable tau. So we'll have the impulse function, or delta function, evaluated at t minus tau. Alright? And so now we can write our result. Therefore, u of t can be, it's no longer approximate, u of t is equal to the integral over all time of u of t, u of tau, times the delta function t minus tau d tau. And this may not seem like much of a result now, but we'll put it to good use shortly. So let's recap. What do we have here? We have devised a method, a means, whereby we can decompose a function u of t into an infinite sum of impulse functions that are weighted according to u of t and time shifted. Seems pointless at the moment, but trust me, it will have significant results. So a little more on the delta function. So when we depict the delta function graphically, this is how we draw it. We put an arrow, okay, an arrow, and it's centered around 0, and it just looks like an arrow pointing up vertically. If I were to depict delta function time shifted by 1, then we would just have a arrow centered about 1, and it would have a weight. I'm going to put 1 next to it. Next to the arrow you put 1. Now if I had say 10 times delta function t minus 2, we would draw that as Still an arrow. We don't care actually how high we draw it. Well, you might, depending on whether you're trying to draw a scaled version. But you always put an arrow, and you'd put 10 next to it, and it would be centered around 2. Okay? So that's how we depict it. But really all we're saying, what we're really saying, is it's an impulse function. It's 0 for all values except for time equal to 2. It's undefined at time equal to 2, but it has an area, if you integrate it over time, it has an area of 10. Okay? Let's recap now what we can say about the delta function. So this is properties of the delta function. So I've mentioned these already. Let's recap. We have the delta function is 0 for all time not equal to 0, right? It is undefined at t equal to 0, and it has an area of 1. In other words, if you integrate over time, it evaluates to 1. This can be summarized by the following statement. Given a function f of t, okay, that is defined at some t equal t naught, we can say that the integral over all time of the delta function evaluated at t minus t naught times f of t, okay, is equal to f of t naught. Okay, let's think about that for a moment. The integrand is the product of the delta function and this function f. The integrand will be 0 for all time except for when the delta function has an argument of 0, right? Because the delta function is 0 for all time except for when it's delta function of 0, and then it's undefined, right? So where does that happen here? Since this is a time-shifted version of the delta function, the delta function is only non-zero at t naught. At t naught, the function f of t has a weight or a value of f of t naught. All right, and so the delta function gets weighted. Basically what we have is we have this. We have the delta function weighted by f of t naught and centered at t naught. That's what the integrand is. That's what delta t minus t naught times f of t is equal to. Okay, and now we're going to integrate that over all time, and it'll evaluate to 0 except for when we cross or integrate over t equal t naught, and of course the delta function has an area of 1, but because it's weighted by f of t naught, we end up with a net result of f of t naught. Okay, so what does this mean? If you integrate the delta function times some other function, then what you get as a result is the value of that function at the time that the delta function quote-unquote fires. Okay? We'll put this to use. Another interesting characteristic of the delta function is that you can show that the delta function is equal to the derivative of the unit step. So the unit step function, which basically is 0 for all time less than 0, and is equal to 1 for all values or times greater than 1, the derivative of that is equal to the delta function. And that should make sense. At time 0, the step function has a discontinuity, right? It goes from 0 to 1. In fact, we say that the unit step is not defined at time 0. it's 0 for time less than 0, and it's equal to 1 for time greater than 0. So we might say it's equal to 1 at time 0 plus, it's equal to 0 at time 0 minus, but right at time 0 the unit step is undefined. And since it steps a finite amount in 0 time, the slope or derivative of that would be infinite. So in the notes there's actually a proof of this. I just wanted to point it out. So we can also say that the integral of the delta function, okay, is actually, let's do it this way. If we write the integral of the delta function of tau, d tau, and we integrate from minus infinity to t, that's equal to the unit step function. Okay, and I'm using 1 of t for the unit step here because sometimes they use s of t, other times they use u of t, but we've been using u of t as the input, so I'm going to use the notation 1 of t for the unit step. Okay, now we are ready to look at convolution. All right, so the idea of convolution is really where we're headed, because what we're really after is an alternative mechanism to predict the response of a system, an LTI system, given what we will call the impulse response of the system. So you may be given a system description that's a differential equation, but suppose that you didn't have a mathematical model for your system. It was actually a physical system, and all you could do is test it, right? You just, well, we could hit it with this, we can apply this sinusoid, we can measure its response to different inputs, and that's how we're going to describe the system. We don't have a mathematical model for it. We don't have a differential equation. So one idea is that you could hit a system, or you could drive a system with an impulse. Now I just said, we have a physical system, and I also told you that this delta function is a mathematical construct. It doesn't exist in the real world. Right? However, you can actually approximate an impulse. Okay? For instance, they'll actually test bridges, or structures that might be prone to different vibration modes. Say a bridge, right? The Tacoma Falls bridge, classic bridge that actually started oscillating due to the wind frequency and eventually collapsed. You can test structures for their different modes of oscillation, and the way they'll do this, they actually will come out and strike these structures with a hammer. And the striking of that structure is very much like an impulse. It has not infinite, but it has a very high amplitude, and the strike lasts for a very small amount of time. Okay, and depending on the size and the dynamics of your system, you might actually be able to approximate your striking the system as being an impulse. For instance, if it's a slow responding system and you can strike it in a couple milliseconds, that might very well approximate a zero time width impulse. So we're going to play in the theoretical or mathematical world here of just, hey, we're going to hit it with an ideal, truly an impulse function. But know that in the real world, you can actually approximate an impulse with something that is finite in duration and finite in amplitude, but is close enough. Okay, so here's the problem. I've got an LTI system. I don't know its mathematical description, but I can actually measure how it responds to an impulse. Maybe I have that, maybe I'm given that impulse response mathematically as a function, or maybe I'm in the lab and I can measure it. But what we're going to define is the impulse response, what we call the impulse response of the system, and we define it as h of t. So the notation we've used before is that we think of the system t. In fact, let me rewrite this as a system t. It's LTI, all right? But we'll say the output y of t, the input u of t, and we'd say y of t is equal to the transformation, if you will, of u of t by the system t. And we'll do this capital T squirrely brackets u of t. Well, we're going to define h of t is defined as the transformation of an impulse through our system t. Okay? And the objective here is that, assuming that you do have h of t, which we don't know how to get that yet from the differential equation, and we will show that if you do have the differential equation, you can actually arrive at the impulse response from that. But sometimes you're given just the impulse response. Sometimes you just measure that in the lab. If you have h of t, the goal is we want to be able to calculate the response of the system to any input, even though the only information we have is the response of the system to an impulse. It's a really powerful technique. So let's consider some scenarios. So if I stimulate the system with the delta function, I'm going to get a response h of t. By definition, that's what we're defining h of t as being. If I scale my delta function by k, I'm going to get a response k h of t, right? This is the benefit of working with LTI systems. If I scale and I time shift my impulse striking the system, I get a response that is scaled and time shifted as well. And that's again due to the time invariance characteristic quality of our LTI systems. So now what we're going to do is we're going to use those properties, and we are going to consider what if I strike the system with, or stimulate the system with a u of t, all right, where u of t is going to be equal to the limit as delta goes to 0 of u p of t. All right, this is what we've done before. So let me write this out in its completion. What is u of p? It's the infinite sum from n equal minus infinity to infinity of u of n capital delta times 1 over delta p sub delta t minus n delta times delta. Okay, if this is strange to you, go back and look at the lecture previously and where we derived that. I can rewrite this sum one more time, and we're going to harness what we've learned, or what we have established about the delta function, the impulse function. I'm going to go ahead and replace this term right here, 1 over capital delta p sub delta. That is the impulse function, right? In the limit that capital delta is going to 0, that approximates the delta function. So because we're doing in the limit, I can go ahead and replace that. And so I will write delta function, little delta, t minus n delta t. And that whole thing post-multiplied by delta. Okay, nothing really new at this point. All right? We're just restating what we have derived previously. But now is where we will combine this with the notion of superposition and our definition for what is the impulse response of a system, of an LTI system. So here let me take this statement right here, okay? Let me rewrite it with terms that are closer to what we now have for our u of t. What if I have not k delta t minus t naught? What if I have u of n capital delta times our delta function, but argument t minus n capital delta? It's exactly the same thing as what we had right here. I'm just using different names. right, for k and t naught? Well, I get u of n capital delta times h, the impulse response, right, the response to an impulse, shifted by n capital delta. And so let me use that down below. Let me substitute that in here. Well, I'm not going to substitute. Let me use that result to actually write an expression for y of t. If u of t drives our system t, then the response is going to be equal to basically an infinite sum of all of the individual inputs, right? What are the individual inputs? I have pulses. They're time-shifted pulses and they're weighted pulses. And I can write what the response is to any one of these pulses. Here's one pulse. Here's what its response is. So here I will write this infinite sum of responses. It'll be over n equal minus infinity to infinity. And here I'm going to replace what I'm summing with, if I put in a u times delta function, right, then I get a u times impulse response function, right? So let me write that in my sum now. So we'll have u of n delta times h of t minus n delta, and then the whole thing is post multiplied by capital delta. That's still there. Okay? And we're back to the situation where when you take the limit of some function f of n delta and you multiply it times delta, right, and it's an infinite sum, in the limit that delta goes to 0, this reaches or approximates or converges to an integral. Okay, so we'll have the integral of f of tau d tau. So let's rewrite that. So we can say y of t is equal to the integral from minus infinity to infinity of u of tau. Remember that n capital delta gets replaced with the continuous variable tau, times h, function of t minus continuous variable tau, times our differential d tau. And here we have arrived at what we call the convolution of our input with our pulse response. So let me redraw our system as in the block form. And in the block, instead of writing h of s or LTI, I'm going to actually put h of t. All right. Now, don't be confused. I'm not saying y of t is equal to h of t times u of t. No, no. Actually, we use a different operator symbol. We say that when you operate on u of t and h of t in accordance to this convolution integral, we'll use the symbol asterisk or the star kind of thing. We'll say u of t convolved with h of t. All right. And so I can write this y of t is equal to u of t convolved with h of t. And when you see this operator, this star or asterisk, it means convolution. It means you are convolving u of t with h of t. Now you can check out the notes. and see that actually convolution commutates. Convolution commutates. So we can say that u convolved with y, okay, of t is equal to y of t convolved with u of t. So you need not worry about, is it, if you write u of tau h of t minus tau d tau, okay, or u of tau minus, u of t minus tau times h of t, h of tau. These are equivalent. You don't have to worry about which goes where. Alright, so just to recap, what we have found is that if you decompose an input u of t into an infinite sum of weighted and time-shifted impulses, you can use that decomposition to reconstruct the output or the response of a system to that input by taking the convolution integral of the input u of t with the impulse response of the system h of t. Now, we haven't yet found or shown how we can come up with h of t, the impulse response of the system, but it's very simple to do, and it is very closely related to the homogeneous response of a system. Okay, so this is a powerful technique. It's an alternate method of finding the response of a system to an input, especially in cases where you don't have the differential equation and you may only have the physical system, or maybe some numerical simulation or something that gives you what the time domain, the impulse response is. You can use that h of t to find the response of the system to any arbitrary input u of t. Okay, at this point I want to switch over to the notes that accompany this lecture, and I'm on page 19. This is a set of notes that cover continuous time LTI systems. And so at the beginning of, or bottom of page, bottom of page 19, we have the first example, and we'll work through a couple examples to show you what convolution looks like. So let's suppose we have a system where we have an input f of t and an output y of t, and actually the system has an impulse response of delta t. So actually we don't even have to think about this being a system. Let's just play around with how do you actually evaluate how do you do the convolution integral. So we want to convolve the delta function with f of t. So what you do is, using this form here, we are going to write an integral that goes from minus infinity to infinity, f of tau times the delta function evaluated at t minus tau. We could have also done f of t minus tau times the delta function tau. We could have put that as the integrand, and that would have worked just as well. So we're convolving an impulse centered at 0 with some function, and here I've drawn a function. Looks like it's a ramp up and then a ramp back down centered at 1. Alright, and what does this integral evaluate to? Well, the function, the integrand, will be non-zero only when the delta function fires, right? And the delta function fires at t equal to tau. So the result of this integration is that we get back the function f of t evaluated at t, right? So in this case, if we were actually looking at a system response, we would say, okay, our system is a system that has an impulse response that is a delta function, all right? And so if h of t was actually equal to an impulse function, then if you put u of t in, you're going to get u of t back out. And let's look at another example here. In this case, we have an impulse response for a system of e to the minus 3/2 t. So that would, if we actually plotted h of t over time, basically it's an exponential decay, right, with a time constant of 2/3. Okay, and we're going to input a step to this system. So we want to put in a step, and we're going to drive the system with that, and we're wondering what the output is. Okay, so y of t is going to be equal to the convolution of a step times this exponential decay. So here we're going to plug and chug with this. So we write y of t is equal to the integral of h of tau times u of t minus tau. Now u of t minus tau is going to be equal to 1 or 0, depending on the argument. So it's going to be 0 whenever the argument is negative. All right? So when does it become negative? It becomes negative when tau equals time t. So if tau is less than t, then the argument is positive and it evaluates to 1. So what that means is, go back here, is that this fact here actually goes and informs or changes our upper limit of integration. Because, for instance, let's see we're integrating beyond t, time t, we go to t plus 1. Well, when you evaluate u of t minus tau at t plus 1, you get u of t minus 1, which is u of minus 1. And u of minus 1 is 0. Okay? So the integrand is 0, so no point in integrating beyond that. And notice that now we have, right here we just have 1. Our u of t has been replaced by 1. So we're simply going to integrate to t. We're going to integrate the impulse response to t. Now we have the lower limit here also set to 0. Why do we set that to 0? Well, for tau less than 0, put this over here, for tau time less than 0, our impulse response is 0. Right? We've defined the impulse response to be an exponential decay for time greater than or equal to 0. So there's no point in integrating for negative taus, because at that point the integrand is 0, because h of tau for negative taus is 0. So we limit it on the bottom side to 0, and we bottom end to 0, and the upper end we limit it to t. So now we're simply integrating e to the minus 3/2 tau, and you can evaluate that, and you find that the y of t is an exponential function, 1 minus e to the minus 3/2 t, and it looks like this. Okay. Okay, let's look at one last example. And here we have the same impulse response as before. Okay, but what's different is the input now is the sum of two unit steps. I guess in my notes I'm using what is that? C, lowercase c, is the unit step. So what we have for the input is it steps up at 0 to 1, and then we're going to subtract a step at 2. Okay, so you end up with something that looks like this. From 0 to 2 has an amplitude of 1, but beyond 2 and less than 0, it's 0. Okay, so what does the response look like? I have the result plotted down below, and so you can see that at time 0 you get the output that starts rising exponentially, and of course it would tend to go up like this, but then the input goes away and so it comes back down. So how do we evaluate that? Well, we're going to evaluate several integrals, all right, over different periods of time. So from time 0 to time 2, u of t is equal to 1. All right, so here's the first integral that covers time 0 to time 2. Then for time greater than 2, what we have to do is we start off with what we've accumulated from time 0 to time 2. So that's why we have the first term. And then now we're going to subtract what we have from time 2 on. Okay, and the reason for the minus sign is because at time 2 we subtract a unit step. And I won't go through the math, you can work through that, but you end up, the final result is that from time 0 to time 2 you have this exponential which looks very much like, in fact identical to what we had up here in the previous example, but that's only valid until time 2, and then from time 2 on we start with what's been accumulated up through time 2, but we subtract then the second term, and that captures the remainder of our response from time 2 on, where it goes back down to 0. Okay, as a final demonstration, I want to show a little animation that may help better explain convolution. So what I've done is written the two equivalent forms here for convolution of the impulse response with the input. Now in the example here that was worked out in the notes, the first integral is what is being evaluated. But in the animation I'm going to show you, it just happens that I evaluated this one, so I didn't want you to be confused. So what I want to do before showing you the animation is consider this h of t minus tau. Okay, if we have h of t, if I plot that and it's just this exponential decay, it's not a very well drawn one, but okay, exponential decay. What does h of t minus tau look like as a function of tau? Okay, what does that look like? Well, it turns out it's actually a flipped, reversed version, where at tau equal to t, the argument is 0, right? And at, for instance, tau equal to 1 less than t, it would evaluate, basically a value of h of 1, right? And so it's a flipped version of h of t. And what we're going to do is, if you have an impulse here, this step that lasts for some amount of time, goes from 0 to 1, okay? What we're doing is we're going to evaluate the integral of the product of these two functions at different periods of time. So here's 0. This is now time 0. If I want to know what is the value of the output at some time, let's say this is actually minus 1 right here. All right, at time minus 1, the way that we find what the output is we integrate the product of this function h of t minus tau times this input, which is a pulse. And you can see in this case they don't overlap at all, so the product is 0. But if I were to now ask what is the output at time 1/2, okay, what I would have is this is 0, this is 1, this is 1/2, right? And the output of the system at time 1/2 is equal to the product of these two, or the integral of the product of those two. And you can see in this case that there is an overlap in these signals where there will be a product, and the product would occur right in this region right here. And so it's actually going to be the area of this h of t scaled by the input, which is a constant equal to 1 in this case. All right. So let me show you this animation, and maybe with that introduction, the animation will allow you to better visualize what is going on. This comes from MathCAD, and perhaps I'll post the link to the MathCAD file. I think it was made in MathCAD 15, and you can actually play around with it in MathCAD if you like. So here's the animation. I think, let me see. Yeah, I may pull up the MathCAD file afterwards. Let's play the animation. Now what I'm showing is we're evaluating, so the horizontal axis is time. And at every moment in time, so as this is kind of stepping discretely in time, you kind of freeze frame that, and you say, okay, at time, here it looks like I have at time, oh, I drew that wrong, by the way, earlier. I guess this is actually 2, right? Because the pulse lasts for a width of 2. So here we're frozen at time t equal 2, and we're saying, what is the output? What's y of 2? Well, y of 2 is actually the integration of the product of this flipped h of t with the input. And this solid area that is shown here in orange is, well, times 1, in this case, the input. That integration, that area, is actually what y evaluates to. Y is being plotted, basically, the current value of y is plotted as this dotted red line. So as I play it again, watch how the red line will go up beginning at 0. Here it goes at time 0, boom, starts going up, and then it falls back down as time evolves further. Right? And that corresponds to this rising here and this coming back down. Okay. Okay, here I've pulled up the MathCAD file that produced that animation, and there's a little more information in here that I'll just scroll through right now, and I'll try to put a link, including a PDF output of this file, online as well. So again, we're looking at this minus 3/2 t exponential impulse response. So here's the impulse response, h of tau, okay, and here is h of minus tau, it flips, and here is h of 3 minus tau, where it's flipped and it's shifted in time. And then here is our defined input, basically a pulse of width 2, amplitude 1, and centered around 1. And now we're going to look at the product of this input u of t times h of tau minus t, and we're going to do it at time 0.1. And you see there's a little overlap shown by that orange. And now we do it, we're going to do it again at multiple times. So at time 0, there's no overlap, and the integral over here actually evaluates to 0. That's the convolution integral. Now we're going to evaluate it at t equal 0.1. So there's just a tiny bit of overlap. So the area then is 0.093. We move a little further in time at 0.5, and there's more overlap, more area. The convolution integral evaluates to 0.352. These numbers are the actual output y of the system. When you get to time 2, you get the maximum output, right? Maximum overlap here, and this evaluates to 0.633. And it keeps going on to show a couple more of these. And in the end, here's the actual convolution evaluated for a continuum of times from -10 to +10.